Good day, everyone. I am Isaiah Tupal, and for this next few minutes, I will be presenting our project implementation of a Filipino Sign Language recognition model on a Raspberry Pi 3 using convolutional neural nets or CNN and TensorFlow Lite. So let's have a bit of a background. Uh, Although this is common sense, the most common form of communication is verbal communication. The issue with this is that not everyone can communicate using verbal cues, especially particularly or specifically the deaf community. The deaf community communicates via visual cues such as hand position and facial expression or signs. And this system of communication is called sign language. The thing about sign language is that there's a lot of variation across the globe. Americans use American Sign Language, Chinese use the Chinese Sign Language, there's also the Indian Sign Language, and for the topic of this project, there's the Filipino Sign Language that is signed by Filipinos. The thing about sign language and computation is that with the increase in hardware and research, there's a new field that was birthed, which aims to narrow the gap between those who are of hearing and those who are deaf. That is the sign language recognition research. For the Filipino version of sign language recognition research, there are several studies. One used Kinect to classify or recognize 10 signs, and this yielded an accuracy of 95%. The drawback of using Kinect is that you need to set up sensors to capture the sign. Hence, most of the research now focused on visual-based methods such as using the camera. And a popular model that uses the visual-based approach is CNN or convolutional neural network, as seen on the second project. Here, the authors were able to recognize 10 signs with an accuracy of 86.7%. And they use the ResNet. It is a kind of, it is a version of a CNN. And these research or models show that there's potential to FSL recognition research. However, these models are usually large and complex. For example, the state-of-the-art model, here the skeleton-aware multimodal SLR model, is around more than a gigabyte. So that's just the model, not including the data. And for this to actually run, it requires powerful hardware. Yes, complex and heavy architecture does bring good results. However, there's still a need for these models to run on low-end devices. For example, here's a scenario. You're in a remote area with no internet and no access to an expensive equipment. How will you send or how will you infer on a data if it's on the cloud and you have no access to the internet? So that's a specific scenario. And researchers were able to notice this gap and these specific scenarios. So they created a new subfield in machine learning, which is tinyML or tiny machine learning. And the goal of tinyML is to create algorithms or device optimizations for models to run on low-end devices, such as on the right. This is a Raspberry Pi. It is actually what is used in this project. Now, I mentioned earlier, most SLR models use CNN. The reason is that it is just good at image or video or just vision-based application. The problem is that the computational complexity is high. Hence, there are works to create CNN models that are not as complex as other models. An example of this are the mobile nets and the efficient nets. So these two are CNN models that are much more smaller compared to their other CNN counterparts. So as mentioned earlier, tinyML, the goal of tinyML is to run on resource-scarce device. Since, well, the goal of this, or a good advantage of this, is that there's no need for a cloud to shoulder the computational cost. That's what is done in other applications. And also, you don't need the access to expensive hardware to do inference. And a popular framework in converting complex models into more efficient ones is the TFLite. Now let's go to the methodology. The dataset is comprised of frames from various tutorial videos shown here. And there are a total of 29 classes, 26 letters, 2 non-letters, so this is space and delete, and 1 non-sign. Basically, there's no sign in the image. And the collected frames will be used to train for models. So these are the mobile nets, or the 3 version of mobile nets, and EfficientNet. After training, although these are small versions and more and efficient versions, they will be then converted into TFLite, since it is what lets the models run on the Raspberry Pi device. So there will be so TensorFlow Lite or TFLite will be used to convert these models. And to evaluate the performance, 4 metrics will be used, which is precision, recall, F-score, and accuracy. So precision, recall, and F-score, basically they just determine how the model is able to discern true positives and true negatives, false positives, false negatives. However, for the overall performance of the model, accuracy will be given the, I'd say, much more weight compared to the first 3. Aside from the performance, the size and the speed of inference were also recorded since we are running this on a low-end device. And here are the results. So a total of 200,000 images were collected, and 70% were used for training, and 30% are used for testing. And here are the results of the training and testing. As you can see, the thing about precision, recall, and F-score is that um, they all measure how the model is able to discern true positives and true negatives. Actually, as shown here, the metric is close to 1. So 1 means it's really good at what it's doing, and 0 meaning it's really bad. As you can see, in the scale between 0 to 1, most of these score metrics are near 1. Some are even 1. So this shows us this model is very accurate in the dataset it is trained. And here are their accuracy. EfficientNet being the most accurate, followed by MobileNet. But we are not interested in the complex models. Although these are efficient, they are still considered too complex for the Raspberry Pi. Hence, these models are converted to TFLite or TensorFlow Lite version. So it will convert these machine learning models, although they're efficient, they're still not tinyML. For them to be tinyML, they have to be converted using TensorFlow Lite. And TensorFlow Lite or TFLite claims it can compress 3 to 4 times the original size. It did not really do that to the 4 models. The hypothesis here is that since they're already made to be efficient, there's not much really you can do to make it more efficient if the goal of the model is that it's already efficient in the first place. So these are the size of the models, pre-conversion and post-conversion. Not much difference. Now for the performance. It's terrible. For MobileNet V1 and V2, so as mentioned earlier, the PRF or the precision recall and F-score, they're scaled from 0 to 1. Most in MobileNet V1 and V2, most of it is in 0. So these are the classes, and these are the metrics. they're terrible. MobileNet V3 and EfficientNet, however, did fare better, and we will see that when we view the confusion matrix. As there's a bias to the second to the last class, so that's actually nothing. So most of the signs are classified as nothing when these models are converted to TFLite. So the one on the left is MobileNet V1, the one on the right is MobileNet V2. There's a different story in MobileNet V3 and EfficientNet. In MobileNet V3 and EfficientNet, they were actually able to classify the signs. And here's the summary. So you can see EfficientNet is just way more accurate compared to the 3, although MobileNet V3 can stand on its own. However, there is still a case here. Since on the right, you will see the inference time. So this is the inference time in classifying the testing images. So all of the testing images, and then the time was recorded. As you can see, although EfficientNet is much more accurate, there is still a case for MobileNet V3, and that is, it's just much faster than EfficientNet. So, preferring one over the other boils down to the use case of how fast they want it to be and how accurate they want it to be. And that's actually the conclusion. So in the conclusion, only 2 of the 4 models work when converted to their tinyML versions. MobileNet V3 and EfficientNet. And EfficientNet is much more accurate than MobileNet V3. MobileNet, however, is just faster in inference. And as for further recommendations, we recommend this to extend to include other models. So there are new models that were not considered here. It's just very, very new models that came out a few months ago. Another good another way to extend this research is to actually apply this to real-time recognition. So here we have a data set and then we classified it and we use that as a metric. Another way to extend this is to use a camera system with the tinyML and the resource-scarce device itself. And so that's all for this project. I hope you enjoyed our presentation, and good day to everyone here in this audience.